Hello, my name is Michael Awaje, and today I will be discussing the pathways our bodies use to produce ATP from the complete breakdown of one molecule of glucose and one molecule of fat. I'll go over the key steps of each pathway, the ATP yield of each pathway's interaction across exercise intensity and duration, the limiting factors of each pathway, and the real-world applications of each pathway. Now let's delve into the fascinating world of glycolysis, a fundamental process in cellular energy production. Glycolysis is the breakdown of one molecule of glucose into two molecules of pyruvate. This process is anaerobic and occurs in the cytoplasm of the cell. The pathway consists of a series of 10 enzymatic reactions, each playing a crucial role in extracting energy from glucose. As glucose is converted into pyruvate, there is a net production of two molecules of ATP and two molecules of NADH. This initial phase sets stage for the subsequent energy extracting processes in the cell. In certain conditions, pyruvate generated by glycolysis can be converted to lactic acid. This process is known as lactic acid fermentation and is an alternative pathway when oxygen availability is limited, providing a rapid source of ATP. The beauty of glycolysis lies in its adaptability to different exercise conditions. During high-intensity, short-duration exercises like the one seen here, glycolysis takes center stage as it provides a rapid source of ATP, crucial for short bursts of energy. In prolonged moderate intensity exercises, glycolysis remains active but starts to share the spotlight with other pathways like oxidative phosphorylation, ensuring sustained ATP. While glycolysis is versatile, it does have limitations. One key limitation is its reliance on substrate availability. If glucose is scarce, the rate of glycolysis may be compromised, impacting ATP production. Now let's transition to the next crucial step in cellular energy production, the citric acid cycle. The citric acid cycle, also known as the Krebs cycle, is right after glycolysis, where each pyruvate produced from glycolysis enters the mitochondria. Here it undergoes a conversion to acetyl-CoA, a pivotal molecule for the citric acid cycle. The citric acid cycle is a series of 8 enzymatic reactions, beginning with the combination of acetyl-CoA and oxalose acetate to form citrate. Through a series of transformations, citrate is gradually broken down, releasing carbon dioxide and electrons in the process. For each round of the citric acid cycle, 3 molecules of NADH, 1 molecule of FADH2, and 1 molecule of ACP are produced. Keep in mind, each glucose molecule generates 2 acetyl-CoA, contributing to 2 complete cycles. The citric acid cycle plays a crucial role in energy production during endurance exercises. However, during high-intensity, short-duration exercises, the reliance on the citric acid cycle alone might be insufficient to meet energy demands. One limitation is the availability of oxygen. If oxygen is limited, the efficiency of the citric acid cycle is compromised, impacting ATP production. The high-energy electrons produced during the citric acid cycle are vital, as they will be used in the next stage, oxidative phosphorylation. The high-energy electrons generated in glycolysis and citric acid cycle are transported through the electron transport chain, located in the inner mitochondrial membrane. This transfer of electrons establishes a proton gradient across the membrane. The flow of protons back through the ATP synthase drives the synthesis of ATP through a process known as chemiosmosis. This is where the majority of ATP is generated, providing a more sustained energy production method. Oxidative phosphorylation shines during moderate, long-duration exercises, where a steady supply of ATP is crucial for endurance. The reliance on this pathway becomes more prominent as exercise duration increases. Oxidative phosphorylation is not without limitations. The process heavily depends on oxygen availability. During intense exercise, oxygen demand may outpace supply, leading to a phenomenon known as oxygen debt. This can limit the efficiency of oxidative phosphorylation and ATP production. Here we see another more detailed visual of the process in the mitochondrial membrane here. But now we'll explore another vital pathway in a cellular energy production: beta oxidation. Beta oxidation is the process by which fatty acids are broken down in the mitochondria to generate acetyl-CoA, the key player in the citric acid cycle. Each cycle of beta oxidation results in the production of acetyl-CoA. And not just only acetyl-CoA, NADH and FADH2 as well. For each round of beta oxidation, the subsequent citric acid cycle and oxidative phosphorylation contribute to the production of approximately 14 ATP. This includes ATP produced directly in the citric acid cycle and the additional ATP generated during oxidative phosphorylation through the transfer of electrons from NADH and FADH2. Beta oxidation becomes particularly crucial during endurance exercises or activities where the energy demand is sustained over a long duration. Fatty acids serve as a rich energy source, contributing to a more prolonged and steady ATP production compared to the other previous pathways we discussed. While beta oxidation is efficient, it's not the go-to pathway for high-intensity, short-duration exercises. The breakdown of fatty acids requires more oxygen compared to glycolysis. In situations of limited oxygen availability, reliance on beta oxidation may be restricted, impacting the production of ATP. Now that we've explored the intricacies of glycolysis, the citric acid cycle, and beta oxidation, we'll uncover how these pathways collaborate and their real-world implications. In the body, these energy pathways don't function in isolation. They intricately collaborate, adapting to the varying demands of physical activity. For example, during moderate intensity exercise, the body might simultaneously engage in glycolysis, beta oxidation, and the citric acid cycle to optimize ATP production. Understanding these pathways is crucial for designing effective training regimens. Endurance athletes may benefit from enhancing beta oxidation for sustained energy, while sprinters might focus on optimizing glycolysis for quick bursts of power. Despite the efficiency of each pathway, relying solely on one isn't practical for diverse physical activities. Our body's ability to adapt and seamlessly switch between these pathways ensures a continuous supply of ATP, making us versatile in meeting the energy demands of various exercises. So, in conclusion, we've journeyed through the intricacies of cellular energy production, from glycolysis to the citric acid cycle and beta oxidation, witnessing how each pathway contributes to the production of ATP. These pathways dynamically interact, adapting to the specific demands of exercise intensity and duration. We've seen the real-world application, understanding how these pathways influence training strategies and athletic performance. Whether you're an endurance athlete relying on beta oxidation or a sprinter maximizing glycolysis, the body's ability to coordinate these pathways is key. In closing, it's the versatility of our energy system that empowers us to engage in a wide range of physical activities. No singular pathway can meet all demands, highlighting the sophistication and adaptability of our bodies. Thank you for joining me in this exploration of cellular energy pathways.